Now, we're talking about composing functions. Now, let's say we've got a function here, f, whose domain is set x, and we've got another set here, which is y, and fx in that direction. And then lastly, we've got another set there, which you could name z, and we've got another function acting in that direction. Now, you notice that if we've got x here as an input to f is in this position, and let's say this function here is g, then we're going to have an output here, which is in the range of f, calling it f of x. Now, if it now have g as a function whose domain is the image or is the range of f, then you can sit in this side with a value g of f of x. It's a bit crowded there, but you can see it, isn't it? Okay. So now, then once you've done that, we can actually define another function which picks this x and send it direct to that value there. And then let's call that function h of x, and we're going to denote it this way. We're going to put it g, small circle there, f to say g composed with f. Now, if this function picks x from the original domain x there, what is going to happen is it's going to evaluate first of all f of x, then evaluate g, evaluate at f of x, like you see there in the schematic there. Then this function here is going to be called the composite function. It's a result of composing two functions. Am I making myself clear? Okay. Now, once we're there in that idea of composing two functions, maybe let's get an example. All together, let's get an example. Let's say we've got f of x being a function which is 1 over x, and we've got g of x being equals to simple function like x plus 2. Now, if we're given a task now to find the h, we have to follow this kind of process, isn't it? So now, we can say h of x is going to be equals to g of f of x, which is equals to g, then I put still the square brackets there. Now, what am I going to throw in there? I'm going to throw the expression for f altogether, which is going to come in there as 1 over x. Now, I told you the other day that you must read this, you must have what the function is having there in brackets, call it its argument, isn't it? It doesn't matter the color or the shape of that thing, it's called the argument of that function, isn't it? So, you must now listen to G. Listen to G. G is saying, I pick my argument, I add it to 2, isn't it? So when you read that G that way, when you come here, you will say now, equals my argument, which is 1 over x, plus 2, altogether. Now, if you understand that simple example, I'm expecting you to do more complicated examples, as long as you know how to read the function statement back to yourself. Altogether. Okay. Now, let's give another example here. Maybe let me just clean the top here and say, oh no, let me just roll this thing up. Oh, it's just right at the end. Sorry, I think I'm going to roll it up that way. fun. Okay, maybe let me just erase it. Let's control T. Right. What was our F? Our F was what? 1 over x. Our G of x was equal to x plus what? Plus 2. Now, we did H, which was G composed with F, and then we did that it was H of x equals to what? G of F of x, and then that equals to G of 1 over x, which gave us that as what? 1 over x plus 2. Is that right? Now I want to give a function here. Let me say k of x, which is equals to x squared plus 3x. Are we together? Okay. Now let's say we want to compose to get another function, let's say L of x, and that function L of x is equals to kg composed with k. Can you now expand the expression for L of x, please? Do it for me. Quickly put your pen against the paper and quickly do it. I want to see everybody writing, doing something. I'm just asking you to mimic what you have done before and just have a feel of it doing it yourself. Alright, can you tell me what to write? Please use the square bracket. Tell me what to write and say square bracket what. What should I write there? G square bracket. Yeah. K at x close square brackets. Then that is equals to what? G. Then square bracket again. What do I put inside there? X squared plus what? Plus 3x close. Then that is the argument of G, isn't it? What does G do? What does G do to its argument? It adds 2. So you're just going to copy that as it is plus 3x and just add a 2. Out together. Okay. So now let's now do the reverse now. Let's do the other order now. Let's say we wanted to have n, a function n, which is equals to k circle g. Which function is going to act first on x? You see, when it's right like this, it's k which acts first on x, isn't it? So here, which function is going to act first on x? G. So now, let's have n of x. How is it going to look like? K square bracket g at x. I'm not trying to say you are always going to use square brackets. You can use any other bracket, but for now I just want for us to communicate in a kind of same tonation, isn't it? Some people can just use any other bracket, there is fine. Then next it will be k. What will be the argument of k now? X plus 2. Then what does k do to its argument? You must be able to talk that back to yourself. K squares its argument, multiplies its argument by 3, and adds the 2 results, isn't it? So what's going to happen now? We're going to have x x plus 2 all squared plus 3 brackets x plus 2. Are we together, guys? Okay. I heard you saying x somewhere there. I hope you corrected it.
Because k is x squared plus 3x.
Yeah. So, but when you write there, you don't write 3x.
Yeah.
Are we together? Yeah. So, I hope you understand what I'm correcting. You can't write 3x because the argument now is x plus 2, isn't it? So I must write 3x plus 2, as in 3 multiplied by x plus 2. So after that, you remove the brackets. I think the first bracket gives you x squared. That is I think now that is a sum of, I don't know, 3x times 2 times x plus ab, isn't it? 2ab plus 4 plus 3x plus 6 altogether. Then that gives you x squared plus 7x plus 10. There's something you must notice there. If you change the order of the composition, you get a different function, isn't it? So in general, it means if we've got a situation like this where we're composing two functions in different orders, we are not going to have k or g equal to g circle k. In general, this equality is not true. It can happen sometimes. That take that as a mere accident. Altogether, okay. Come again? G composite L. Should I explain it? I said if it's like this, K is going to express on the argument X. That's why I'm writing this thing as G of K of X. Now when I'm there now, I need to replace that placeholder K of X by K of X, by the statement of K of X. The statement of K of X says x squared plus 3x. That's why it's sitting there. Then what happens now is the statement of G, which is going to now take over. So the order from G says my argument plus 2. So what is the argument here? X squared plus 3. That is x squared plus 3 plus 2. Is that right? Yeah. Please, it's very important to know how to read that thing properly and know what to do. Because if you don't, then you're not going to do the right thing. Yes? No. We haven't talked about inverse. Please don't use the words which I've introduced in class. Let's just stick to what we're going to get there. Please, we're going to get there. Yeah, we're going to get there. Altogether. Actually, that's my next thing now. Now people are going to say, what is this inverse there? Right. So just hold there. Are we enough with this thing? We know how to do with this thing. Now you go to notes exercises. There are a lot of exercises. They compose this and that, evaluate this after composition, and go into that place. Altogether. Okay. Now let's come to a situation where we have something like this. Actually, what I want to talk about now, I want to talk about what we call inverse. In talking in a common man's language, inverse, I would just say the reverse process. The reverse process, isn't it? That is the language I would talk to my grandmother when I went to school. Okay, so now, let's say we've got a function there, a set, a domain of a function, and another set there, a domain of another function, and then there. Let's just say in case that this is x, and this is again x, and this is y. Now, let's suppose f is doing that there. Then G moves from there to there. Then there is F, there is G, then we got a little x there, our f of x there, our g of f of x are sitting there. Right. Now, if you check what's happening there, if you check f passed from what? From x to y, and the g passed from y to f. I could have I just wanted to be a bit explicit there. I could have just taken g from there back there. Isn't it? Do you see that? Do you see that? My friend, this thing is passing from y to x. But instead of going further in the other direction, it could have just gone back to x. Is that not reverse? I see this one is the Italian getting confused. Please avoid getting confused very easily. Né? Yeah, that's very important. This is x. The same x like that one. Maybe let me use the black ink. People might think that the color makes a difference, but normally color does not make a difference. Altogether, that is x and that is x. So, do you understand now? I say that this transition from x to y, from y to x, I would have just used two diagram and said, go back there, isn't it? Okay. Now, but that's not what I'm interested in. What I'm interested in is, if now I create h such that h that, and I find that if I put this x as an input to h, that is equals to g of f of x, and that is actually x. That is possible, isn't it? Because g is coming back from y going back to x. It could go back exactly to the same x. Is that right? It's fine. Now, and also, if I also find out that if I have f, let me say f o g, let's call this k, and I do the valuation of k, and say k, that is equals to f square bracket g of x, and then I get that I go back to k again, to what? To x. Do you see what's happening there? Yeah. Now, which means I start by g, and then I evaluate f, I still go back to x. Now, when this happens, these two things happen, then we say f is f is an inverse of g. Altogether, f is an inverse of g. And the relationship here is a relationship which is two-way relationship. You are my cousin, I say to you cousin, you say to me cousin. So if f is an inverse of g, g is an inverse of f. And now, if you look at these two things have done, both h of x and the k of x, what they've done, they've taken x to x. You see that this h has taken x to x altogether. Then that kind of a process, we call that kind of a function, we call it an identity function. Identity function. It leaves inputs identical as they were altogether. It doesn't change them. So we call it an identity function. So what am I saying? I'm saying if you compose a function with its inverse, you get an identity. It's just as good as you're doing nothing. You move 1 meter forward, the inverse is to move 1 meter backward. Where are you? You are at 0. Practically you have moved distance 0. Though maybe you wasted time moving forward and wasted time moving backward, you should have just stayed at 0. All together. I hope this makes clear. Is that right? Listen, sometimes when we're teaching mathematics, there are some situations where nature and how things are done in practical life, they offer themselves to be examples. But don't expect that all mathematics will have that kind of tangible examples. Because some examples can be examples within math itself, and they all becomes just thinking kind of abstract ideas, something like that. But again, create things from the abstract. All together? Okay. So some examples are going to be practical, like outside mathematics. Sometimes are going to be within mathematics, and it might be very difficult to take them outside mathematics, maybe to a desk or to a ladder. It's not always the same thing like Pythagoras theorem. You can put a ladder against the wall and they actually show what you mean by blah blah blah. That's right. Good. I hope the idea of inverse is understood, isn't it? And I'll highlight here something very, very important. This idea of inverse is actually what makes the solution of equations possible. Solution of equation possible. There's no solution of an equation which can be carried out without the idea of an inverse. Do you believe that? You don't believe? In other words, now what I want to try to do now, what I want to try to think about now, think about that. If I've got an operation in front of me, like addition, what is its reverse process? What is its inverse, sort of? Altogether. So you will find that most of the operations you've got, not all of them maybe, but most of the operations you've got, they're paired in pairs. An operation, its inverse, an operation, its inverse, square root, things like that, isn't it? Every time you're going to solve an equation which involves a power of x squared, you need a square root. That's what I'm saying, that the idea of an inverse is there, and that's what makes equations possible to solve. Otherwise, they're going to be solved analytically. By meaning analytical, pushing the pen against the paper, transforming the equation using equivalent transformations. Are we together, guys? Okay. So this is the next actually.
The multiplication of a function
Wrong word. I never said multiplication of composition. Good. Maybe when you write it there, G O F, it looks like that O can look like a multiplication sign, like a dot. No, it's not a multiplication sign. It's a composition. So what I mean exactly? In numbers, 2 times 3 is equal to 3 times 2. Why am I talking about that thing? I'm talking about that thing because this thing looks like multiplying from a structural point of view. But when you're dealing with composition, the composition of F with G is not the same composition of G with F. It's not normally the same. Are we together? Okay. But if the functions are inverses, it's going to be the same. Like for example now, K of X and H of X are exactly the same. Because what do? They take X to X, isn't it? Yeah. When you're dealing with composition of a function and the inverse, and that is what happens. Maybe let me emphasize, just put that one there. Now, let me just write there talking about inverse again. Now, if I've got, if f, the function, is it, let me say if G if G is equal to the inverse of F, then we've got this fact. G composed with F is equals to F composed with G, and that is equals to the identity. I'm going to use that ID as an identity function, isn't it? So in other words, we can now replace G with the F second function. Then this becomes something like this. And that is again identity. So in other words, if I have F second function composed with the F picking on X, this is going to be F second function square brackets F of X, that, and then that is going to be equals to identity of X, which is going to deliver us X. How to get it? So in our simple, this part here will simply deliver us X. Even if you change the order, it's still going to deliver us X. All together? Okay. So I think we're going to stop there. Sorry, this is supposed to be inverse, with an E there. Yeah, others are going to stop there. Then next lecture we're going to look at examples of inverses. Then after that, once we have known all these concepts of what is a function, what is an inverse, what is composition of functions, then we're going to look at particular functions, like we look briefly at linear functions, polynomials, exponentials, trigonometric, and so on. Then we'll be now dealing with particular functions, but using all these terms of length. So it's important that the terminology, the vocabulary we have accumulated in these 2-3 lectures must be used, and we're going to use it. Tomorrow we're going to correlate with this and then start on something new, like looking at particular types of functions. Thank you for listening.